If you come to the conference in person, you don't know who you're going to bump into in the hallway. You don't know exactly who you're going to run into at dinner, who you're going to end up sitting across from at the lunch table, but they could be your future collaborator, your future colleague.
All right, let's get started. Welcome to our talk, everyone. Thank you so much for being here. We're going to do quick intros just to start off. I'm Prithvi. I'm currently a software engineer at Microsoft. I've been there for about 2 years. I started right after college. I graduated from Carnegie Mellon. I've also been using C++ for about 2 years. I actually started when I joined Microsoft. So this is my first CppCon. It's my first C++ conference in general. It's also my first talk at a conference, so super, super excited to be here. And I'm here with my co-presenter.
Hi, everyone. Oh, is that too loud? I'm Jasmine. I'm also a software engineer at Microsoft. I've been there for about 3 years. Prior to that, I was in a completely unrelated field, and I switched careers into tech through a coding school called Ada Developers Academy. And this is also my first ever conference that I'm speaking and attending at. So really happy to be here. Thank you.
Okay, let's get started. So in our Back to Basics talk, we're going to be talking about Stringview. So we're going all the way to square zero. We're starting at the very beginning. We're talking about why Stringview exists, what's the motivation for having it. Then we'll talk about the details of it, so how to use it, constructors, where to use it, what problems are you going to run into, etc. And then once we kind of talk about the details of Stringview, we're going to go into some discussion about span. There's some interesting comparisons that you can make between the two, so we'll touch on that. And then finally, at the end, we'll walk through a case study where we can optimize some code using Stringview and using span. Okay, so let's get started with the motivation. So let's say you are writing a function which operates on an immutable string. Typically, you'll add some sort of signature like this, right? This is a function foo. It takes in a const string ref. It works fine in terms of functionality, right? You initialize a string, you allocate some memory for it, and then you call foo on it. It does its thing. If you do something like this, again, foo is still able to do its thing. We call foo on hello, this is a long string. It works fine, but this does memory allocation. And so if you're in performance-sensitive code and you don't want this memory allocation, you may need to modify your code. You may need to write some alternate methods. So you might go ahead and add these to your signature. So here we have a version of foo that takes in a const char star and a length, and then we have one that takes in a const char star, C-style string, but no length. For code reuse, 1 and 3 are going to end up calling 2. So 2 is our more general API. 1 and 3 will compute the length somehow, call 2. So this solves the performance-sensitive problem that we were looking at, but now we lose the niceties of having the string API set. And so that's where Stringview comes in. It kind of gives us a solution to both of these problems somewhat elegantly. So we were looking at these 3 functions. Instead of them, we can replace it with just this one. So now we have our function foo. It takes in just a string view. If we were to implement this just to see how it works, we can implement it as just a function that prints out the inputted string view. And we see that it's actually able to handle all 3 of our previous input types. So it's able to handle a string, it's able to handle a const char star with and without a length. And in all 3 cases, we correctly print out our expected string hello. And so this is convenient, but it also gives us some performance benefits because it does not allocate any memory. And that's because the view here is very lightweight. It consists of a pointer to a string and a length. So just to give an example of that memory representation, if we have a string hello, an example string view is one that points to that first character, has a length of 6. Another is one that points to that second character, has a length of 2, kind of like a substring. A quick note here, we're going to keep reiterating this, we're going to keep coming back to this. Unlike string view is not necessarily null terminated. Of course, I did want to add the asterisk that there are some non-standard workarounds for this, but Jasmine and I work on Microsoft Edge, so we deal with Chromium a lot. And Chromium actually does have a workaround called cStringView that gives us null terminated string views. But for our purposes, we're going to focus on the no null termination guarantee. To dive a little deeper into the example we were just looking at, right, we had our string hello. If we wanted to go ahead and print out some information, which is what we do here, then we can print out the actual contents of the string, the memory location, that hex value, and the length. And then if we wanted to compare it with Stringview, we can create this function. It prints out the exact same 3 pieces of information, but it takes in a string view and then prints out those 3 things. So we said before that Stringview is able to handle all 3 of the input types that we were looking at before. So if we call this print function that takes in a string view on our previously initialized string s, we see that we get the same content, same length, and the same memory location. Because again, we just have a pointer to that original string. The same goes for if we convert this to a const char star. Stringview is able to handle this input type. We print out the same exact memory location. And in our previous example, we had that second string view, which was like a substring. It pointed to the second character and was just a length of 2. And we can do that as well. Here we've passed in the length. And so now in the output, we see EL. We see almost the same memory address, but it's shifted over by 1, right? We see a 9 instead of an 8, and then the length is 2. A quick note here, cout is actually able to understand Stringview, and it prints it out correctly, right? We see the EL, we don't see anything else, that's great. That's not necessarily always the case, right? So here we've used puts, and we actually get ELLO. Does anyone have an idea of what's going wrong here, what the issue is? Exactly, it's going all the way to the null terminator. So this is something to be careful of. Again, we're gonna keep coming back to this, but when you're using Stringview, don't use functions that are expecting a null terminator because you're gonna get weird behavior like this. Also at a high level, we wanna touch on some of the performance benefits. We're gonna do this by looking at string splitting, classic split string type function. It loops over a string, looks for delimiters. When it finds a delimiter, it creates a substring. Works great. Pretend this is a super long string. I know it's just hello, how are you? That's for slide space reasons, but pretending that's a really long string. Functionality-wise, this is fine, right? It's splitting our string, but there's a lot of memory allocation happening because each of these substring calls is causing memory allocation. And so Stringview is a good replacement here. So here we've changed it to Stringview, right? Not much change in the code. We just had to change the input type and the return type. And we get the same functionality, but we no longer have all of those string allocations because now we have a bunch of pointers into our original string. And also, not much had to change, right? We didn't have to change the substring call, nothing like that. That's because the standard library has kept the interface of Stringview very similar to string, and so not many modifications are needed, which personally I think is a bonus for integrating this into our code. I'm going to hand it over to Jasmine for some details.
All right, thank you. Okay, let's quickly talk over the the sound. Okay, so we have a class template here, a basic string view, right? It's present in the header of string view. Here are some of the common type. Am I going in and out or? Yeah. Oh, okay. So here are the common type defs here. We're mostly going to be focused on the first one, basic string view of characters, pretty standard. Okay, let's talk about constructors. So in C++17, we have these 4 constructors here. One that doesn't take in an argument. We have a copy constructor. We have a construct. I don't know what to do to make it not go in and out. We have a constructor that takes a pointer to a character array and a size, and then we have the last one that just takes a pointer to a character array. And this last one we'll revisit in a future slide. So here we don't actually have a move constructor defined. So what happens if we use move? In this example here, we have a string view, hello, and then we call move on it. Because the move constructor is not explicitly deleted, it's just not declared, it just gets replaced with a copy constructor here. Okay, so given what we know so far, we have these 4 constructors. Let's take a look at an example here. So how does the following code work? We have a string, hello, and we create a string view from that string. Does anyone have any ideas of why this works, given that we don't have a constructor that takes in a string specifically? Okay.
We had a,
oh, we did?
yeah.
It's implicitly convertible to a const char star, is that why?
It's because string has a conversion operator to Stringview. And so if you look into the string definition on like CPP reference, you'll see that there's a conversion operator. And it looks something like this. All right, moving on, C++20, we have an iterator constructor. This allows you to create a string view from a range, like if you wanted to create a string view from subcharacters, a subset of characters from like a vector, for instance. So here we have a vector v, we pass in v.begin plus 1, v.end, that gets us HELL. Here, similarly, we have a const x per char array, and we pass in kstring plus 1 and kstir plus 3, and we get HE, and we get HE because the range there is exclusive. And here's some additional details about the overload resolution. We pulled this from CPP reference, so feel free to take a closer look there if you're interested. In C++23, we have the range constructor, similar to the last, but here we can pass in a vector directly like this. We have SV, and we can pass the vector to create a string view from here. What's interesting about this one, if we take a look at the conditions, that last one, it specifically mentions a type that has a conversion operator to a string view. And what this is saying, it says it's not a valid expression, right? So why this was added was to avoid ambiguity with something like string, for example, that has that conversion operator. Also in C++23, we have another constructor to talk about. So let me go back to C++20 code. So if we were to pass in a null pointer into the constructor of Stringview, this would actually compile fine, but crash sometime at runtime. In C++23, if you were to do the same, this would actually fail to compile, and that's because the null pointer constructor was explicitly deleted. But this isn't foolproof. We could do something like this, where we have a const char star, and we set that equal to null pointer, pass that in to the Stringview constructor, and this would actually compile, but crash at runtime. Okay, so another thing to talk about, going back to that constructor I had mentioned in C++17, this one that takes a pointer to a character array. So this one actually calls string length because we don't pass in this size, right? And maybe this isn't ideal, not as optimized. And so how do we remove that? Well, there's actually a literal operator defined for this purpose, defined here. You can use it like so with the quotations, SV. And this avoids that string length usage. You can use it in the following namespace here. And if you're curious why inline namespaces are used here, you can read this post from Howard Hinnant if you're interested. But there is some nuance with using this literal operator. Let's walk through an example. So we have S1 here. And S1 actually constructs the string view using that constructor that we looked at. S2 creates a string view from the literal operator. And you might notice something interesting here. We have some null characters within here. And so at the bottom there, we're printing out the characters and we're printing out the size. Does anyone have any ideas of what we might see for characters or size printed out?
The first one is going to be only 3. The second one is going to be correct.
Yeah, I think I heard some right answers here. Thank you. So yeah, S1 will only see print A, B, and C. It stops at that null character, and the size accurately represents that, right? But for S2, we actually see that all the characters are printed out with no indication that there are null characters in there, but the size actually encompasses the null characters. And so what's nice about using the literal operator, right? It doesn't have to do that string length call, but it does contain embedded null characters. So keep that in mind if you're ever using the literal operator here. Let me pass it back to Prithvi.
Okay, we're gonna do a quick little chat about string view versus string. We've talked about some of these things, right? String owns its own memory, string view does not. String is always null terminated, string view may not be. This is a bit of new information. The data function for string can never return a null pointer. For string view, it can. What that means in practice is if you are trying to convert any piece of code, if you have something like this for string, that works just fine, right? You take the str length of the data, no problems there. But something like this is going to be an issue, right? When you try to get that data from the string view, it may be null. And so now you're taking the stir length of something null, not great. What you can do instead is check that it's empty before using it. And you can use size. So size is able to handle the null terminator problems with string view. And it's better than just using data. You can avoid that stir length call. Also, string is mostly non-mutable, so it doesn't have a lot of the mutating methods that are present in string. Specifically, these are methods that would require the underlying data, like the source data that your string view is pointing to be modified. So string view does have some mutators. These are the 4 that we've highlighted here. 2 of those actually aren't even present in string. And these mutators are the ones that would change the pointer rather than that underlying data. This is just an example of how the remove prefix and remove suffix ones work. Those are the ones that are just not present in string. There are also some other methods that are not present in string view that are present in string that are not related to mutators. The first is cster, which returns a C string. So basically a null terminated const char star. We don't have that null terminated guarantee anymore, so there is no need for this function. Capacity returns the maximum number of characters that the string can grow, can currently hold without having to grow. We don't have that kind of reserve with string view, so there's no need for capacity. And then finally, get allocator returns a copy of the allocator object for strings. Again, we're not allocating any memory, so there's no need to have that in string view. And then finally, we've touched on this one. This was part of our split string example, right? The substir method in string view is O of 1, whereas it was O of n in string because it was allocating the memory for those substrings. And then finally, we just want to talk about the subscript operator, the index operator, and at. In string view, both of these are read-only. That's just because string view can point to string literals, and attempting to update that is undefined behavior. We have a link there if you're interested in knowing more. This is just an example of what that looks like. So reading information at a specific index of a string and writing to a specific index of a string is going to work fine. But if you try to do the same thing for string view, reading is fine. You can print out the information, but trying to modify it is going to result in these errors. And then we also want to highlight that the out-of-bounds access behavior is still similar. We'll throw an exception. The subscript operator will have undefined behavior. All right, to Jasmine to talk about interoperability.
All right, thank you. All right, let's get into string view, string interoperability. So we kind of talked about that string can automatically be converted into a string view, right? We have this example here. We create a string. We can create a string view from that, and that's because string has a conversion operator to string view. But the reverse isn't true. You can't convert string view to string implicitly. It must be explicit. And so if we look at the following code here, we have a string view hello. If we set that equal to a string, this will fail to compile. And that's because there's no viable conversion here. And similarly, in this example, we have a method foo that takes in a const string reference. If we try and pass in a string view, this would also fail to compile with the same error, no viable conversion. So why is this the case? It's because string has an explicit constructor that takes in a string view-like type. And so if we were to, if we were to take a look at this example, we have string view hello. As long as we explicitly call the constructor like so, we can convert that to a string. And if we take a look at this example we saw previously with the method, right? Passing a string view into method foo that's expecting a string, that doesn't work, but as long as we explicitly convert that, that works just fine. But what is a string view-like type? It's a type that can be converted into a string view, but it can't be converted into a const char star. And just to take a look at this little example here, we have this struct A takes in a const string reference. We have this conversion operator to a string view. And so if we were to instantiate A with hello, we could construct a string from that because of that conversion operator. But maybe you're asking yourself, like, why does it need to be explicit in the first place? The C++ standard folks felt that since string allocates memory, the developer needs to be explicit here. But not everybody agrees with this. If you're curious about some of that discussion, you can check out this Stack Overflow post. But we can go into a little example of why it's helpful to be explicit. So here we have foo and bar, they both take in a const string reference. And if implicit conversion was allowed, then the following would compile. We could pass in a string view into foo and bar like so, and this wouldn't, we wouldn't see any compiler errors or anything like that. But the issue here is that this would cause 2 memory allocations, one for each string. But because explicit conversion is allowed, we would see errors, and we would probably do something like this, where we explicitly convert each string view into a string. But then you kind of look at this code and you're like, that's a little redundant. We could probably just clean it up a little. And so here we can just simplify this a little, create a string from that string view once and just pass in that string. So I think the point I'm trying to make here is that it just forces a little bit intentionality behind like the code here. Okay, so we kind of talked about the definition, some general info about string view, but where can we use it? Prithvi kind of touched upon this in the motivation. String view can be used as the function argument to remove the need of multiple functions dealing with strings, like so. Like all of this can be condensed down into a string view. That's pretty nice. And functions that accept a const string reference could possibly be replaced with a string view. I guess it depends on your use case here, but this does help remove that memory allocation, and it would look something like this, right? But there is something to keep in mind, right? If we do this, we kind of have to make sure that maybe that string view doesn't get converted to string later down the line, because then we do end up allocating memory, and that causes us to lose some of that optimization. It does depend on your use case, but something to keep in mind. String view can also be used in const expr functions. It can be used to create compile time string constants. If we take a look at this example, we have a const expr char array, and it can be replaced with a string view. And what's nice about using a string view is that we have this size function. It makes it a little easier to work with, and it removes the need for string length if you do end up converting to string for whatever reason. And so here we have 2 ways, right, to convert to string view. We have the literal operator, and then we have the one that uses that constructor we talked about. And yeah, this last one, maybe it takes a little longer to compile because we do need to call that string length equivalent. So continuing on this const expr sort of discussion, so we have a const expr char array, right, hello, k-hello stir, and we have a const expr string view. We have this method foo that takes in a const string ref, and we can pass in the k-hello stir, right, directly into foo. But when we pass the string view into foo, we do need to explicitly call the constructor on that. And while we do need to explicitly convert that, we do need to type more. It's a little bit cumbersome maybe, but it does end up being a bit more performant because we don't need to call string length like that character array does. But in general, this piece of code here could probably be optimized slightly by replacing that const string reference with a string view, and this would be a little better. Moving on, we have, in some cases, if we want to gain some performance, string view can be returned from functions. Not every function, just in these specific examples, it's probably a good candidate. So if the function is returning compile time constant memory, or if the function is returning parts of the string view that were originally sent in as arguments to the function. So here we have this get const string that takes in an enum, and then we just return a constant string based on that enum value. This is a pretty good candidate for that. And then here we have a split string that takes in a string view, and then we return a vector of string view that's based on that input, right? The thing here to keep in mind, though, is that we do have to guarantee the lifetime of the underlying data, or else we run into issues, which Prithvi will talk about in the problem section. But we might see something like this, where we have this string foo function, and we pass that directly into split string. Well, what does foo return? It could return a local temporary that gets destroyed as soon as it executes, right? And then splitted here, the const out of splitted would just end up referring to invalid memory. So just something to keep in mind. And in general, Stringview is a lightweight view of a string. It's very cheap to copy. You can kind of think of it like an int or a bool, right? We can just pass by value. And here's some links for more information on why this is better. If you're interested, highly recommend you take a look. And with that, I'll pass it back to Prithvi.
Okay, wonderful. All right, so we've talked about where to use Stringview. Obviously, there are also many cases where you should not use Stringview, so we're gonna go over some of the problems to keep a lookout for. The first is one that we've talked about a bit throughout already, but Stringview doesn't have that null terminator guarantee, so you should avoid using it in functions that look for such null terminators. We looked at that puts example earlier. And then also Jasmine touched upon this earlier, but if you're gonna eventually convert it to a C string, you should consider that maybe you want a string all along or a C string all along and not a string view. You don't wanna catch yourself in situations where you want a null terminator or you wanna convert to a string and now you're doing significantly more work and losing all the optimization that we're trying to do here. The other main problem, this is the one that we're gonna dive super deep into, is that Stringview doesn't own its own memory, so you need to be careful with use after free scenarios. So Stringview points to some source data. If that source data gets freed and you're still trying to access things with your Stringview, then you have a dangling reference. That's gonna cause problems. The first instance that we're gonna talk about is assigning strings to Stringview. So say you have a function foo, it returns a string. Something like this is fine, where you have a const.os that holds the result of foo. You try to print it out, that's fine. Something like this, also fine. You have a const autoref or a r-value reference. You're actually extending the lifetime of the returned object from foo. Something like this, where you have an l-value reference, not great. But your compiler is going to tell you that you did something wrong. So I wouldn't necessarily say it's a problem because you're not going to go ahead and push in code with undefined behavior. This, however, is going to cause undefined behavior. So if you try to store that result of foo in a string view s, and that return string ends up getting destroyed at the end of the function, then when you try to access any information of the string view, its original source data has been destroyed, and so you're going to get undefined behavior at runtime. Another problem is returning string view from functions. So this is also something to keep in mind. So if you have a function like this, where it returns hello as a string view, but using the operators that Jasmine was talking about before, that's fine because hello is in read-only memory. But if you do something like this, where you initialize your string, you allocate memory for it within foo, and then you return it as a string view, this is bad because at the end of this function, that s that you created in the middle is going to get destroyed. And so your return string view is now going to be dangling. That memory has been destroyed. Somewhat similarly, if you have a function that takes in a string and then returns it as a string view, something like this works fine, where you allocate memory for that string outside of your function call. You call your function, you store that string view in a variable, you try to access the variable. That's okay. But then if you do something like this, where you call foo on hello in this sense, then the string that gets kind of used here, so the hello goes and it goes into this s input parameter, that string s, that memory is going to be destroyed at the end of the statement. And so again, right now you've returned a string view that is pointing to dangling, is a dangling reference. It's pointing to destroyed memory. Another such case is returning string view from class methods. So here we have a class A. It has this string as a variable within it. And then we have these methods getS and setS. GetS returns a string view of the string that is being stored in S. And setS replaces that string. So something like this, where you have an instance of the struct A, you call getS to get the string view, and then you access it, is totally fine, right? Nothing has gone in and changed the source data in any way, changed that S in any way. But if you did do something like that, you did go in and change that initial source data like this, then you're gonna run into problems. So here we set S, and so now the original string is being destroyed when we set S. And so when you try to access that string view that was pointing to that original string, you get another dangling reference. Somewhat similarly, if you have a function getA that returns a temporary instance of your struct A, your class A, sorry, you are going to kind of run into the same issues where you call get A and then you get S, but then at the end of that statement, your temporary object gets destroyed. The memory that the string view you initialized is pointing to has been destroyed. Another dangling reference. We also want to be careful returning string view from templates. So this is actually an example created by Nikolai. He's actually at CppCon. I think he has a talk after this. He had a book signing earlier. Essentially, that example starts with this. We have this plus operator. It takes in two string views, converts them both to strings, concats them together, and returns a string. So in our case, we have the string view hello. We have the string view world. Those both get converted to strings, they get concatenated together, we print out this string, hello world. So now if we had a template, this is a double template, it takes in some value of type T, and it returns that value doubled. That return type is actually the same as the input type. So something like double of 1, that works fine, right? We pass in this integer 1, we double it, we get 2, we return an integer 2. But in the case of string view, this is actually bad. So we pass in hello, our string view, into this template. It doubles it, right? So we're using that operator that we talked about earlier. So we have hello and hello as string views. They both become strings. They get concatenated together. And so now you have the string hello, hello. And then because the input type and the return type have to match, this gets returned as a string view. And so this is the problem we were talking about earlier, where you're returning a string view from a function, but you've initialized the source data of that string view within the function. And now when the function ends, that hello, hello string has been destroyed, and your string view is once again pointing to dangling. It's pointing to destroyed memory. The fix here is actually to just change that return type to auto. So instead of having the input type and the return type match, in this case, you would pass in a string view and then you would just return a string hello, hello. And that does solve this problem. And then finally, the last problem we're going to talk about is storing string view as a class member variable. So here we have a struct A. Within it, we have a class member variable SV. That string, it's a string view. It gets initialized when you create an instance of this struct. So something like this, where you're creating an instance of our struct using the literal operator hello or this read-only memory hello, that's going to be fine if you create your instances of A and then you go ahead and print out those values, you're going to be fine. Something like this, however, where you create one instance of A using the string hello, you create another instance of A using the returned value of foo, which returns a string, and then you create a third instance of A where you have hello concatenated with world. These are actually all going to result in undefined behavior. Kind of a broken record here, but this is happening because these are all dangling references, right? At the end of each of these statements, that string you're using to initialize your instance of your struct A is going to get destroyed at the end of that statement. And then once again, your string views are pointing to destroyed memory. There are dangling references. So lots of talk about problems. Is there some sort of solution that we can use? Kind of is the answer. So you can catch these issues with warnings as errors. So you can check out Clang's dangling warnings as errors. Here's some examples of how they actually help. We were looking at problems with returning string view from functions. The W return stack address actually solves this first issue. So this is the one where you initialize your string within the function, you return it as a string view, that string gets destroyed at the end, and so now your string view is pointing to destroyed memory. This warning, which is actually a default warning in Clang, is able to catch it and give you this message over here. The other example that we looked at in the returning string view from functions section was this one where we took in a string and then we returned it as a string view. And then when you called it with hello, like it is over there, that string S was destroyed at the end of the statement and we were seeing a crash. If you actually use the lifetime bound attribute that's available in Clang, this is caught by the W dangling warning. In addition to Clang, MSVC also has lifetime rules. We've linked them over there, and they also have a warning, W lifetime, that catches similar errors. That link over there actually has pretty interesting Godbolt links that you can take a look at. So there is a way to catch some of the problems that we're talking about. Okay, so that brings us to the end of our string view slides. So quick breather, mostly for me. Okay, so now we're going to talk about span. So for Stringview, we talked about the motivation, the memory representation, where to use it, and problems with using it. And now for span, we're basically going to go through those 4 things again. So what is the motivation for having span? Let's say we have the following function. It's a function foo. It takes in a C-style array, as well as the length of that array, loops over the array, prints out the values in the array. Then we have a function foo that takes in a C++ style array. It has a length of 5. Once again, we loop over the array, and we print out the values in that array. And then finally, we have foo, which takes in a vector of integers. We loop over that vector, and we go ahead and print out each of the elements in the vector. And so if I initialize this array here, 1, 2, 3, 4, 5, we expect each of these foo calls, when we call them like so, should in theory print out 1, 2, 3, 4, 5. But they don't, right? This first one actually is 0, 1, 2, 3, 4. Did anyone catch my bug? Yeah, go ahead.
Yeah, you need to access the array.
Yeah, exactly. And this very first one over here, right, I'm just printing out I. That actually wasn't on purpose initially, and then we ran the code, caught the bug, and then decided to keep it. And it's just to point out that it's easy to make a mistake in this code, right? It should have been array of I. We should have indexed into it, but we didn't. But in the other 2 examples, right, we were able to print out I. It's a bit confusing. You might make a mistake. The other thing is that it's also error prone because we depend on the caller to provide this valid n that we assume is the correct length here. And so moving forward into the next version of foo, right, array needs an exact size specification. And so while you will make the earlier mistakes, it's not error prone in the same way. It's not usable in the general case. Of course, there are workarounds. You can create a template like this, but this kind of adds to the overhead, the code that you have to write. And then finally, we have vector. Vector doesn't have these 2 problems. It is type safe, but we need extra memory during construction, kind of like we did for string. And so it would be great if we could have some type that was able to consume all of these contiguous containers with a single interface, and that is where span comes in. So now we have our function foo. It just takes in a span of integers. We loop over the span, and we print out all the contents. It actually is able to handle all 3 of the previous input types. So we have our C-style array, we have our C++ array of multiple lengths, and we see that they both work. And then finally, we have our vector. And in all the cases, we print out exactly what we expect. And so this is great because span has given us a single representation for different types of contiguous sequences of elements. It helps us kind of decouple the interface from the actual type of contiguous sequence, right? We were seeing 3 different types over here. It's able to handle all 3 of them. And also, just like Stringview, it's lightweight. It doesn't allocate memory. It only holds a pointer and a length. So we'll dive a little bit deeper into that. I just wanted to point out that this was the header that was added in C++20 for span. So the memory representation, I said just like Stringview, it doesn't allocate memory because it only holds a pointer and a length. So what does that actually look like? Here we have a vector v. It has just the elements 1, 2, 3 in it. One possible span points to the first element and has a size of 3. With string view, we also saw that we could have like a substring as a string view. You can do the exact same thing for span. So here we have a vector with 1, 2, 3, and 4. We actually have a span that points to the second element and has a size of 2. In these examples, we are showing a dynamic span, right? So dynamic spans are just ones where their size is not fixed. You can like add and remove elements. There are also fixed spans or static spans. These fixed or static spans, their advantage is that you only hold a pointer. They don't hold that size variable because the length is available at compile time. And then finally, we talked about how string view was mostly non-mutable, right? You could never change the underlying data, the source data. That's not necessarily the case for span. So for span, we have both const spans and non-const spans. So the underlying container data cannot be modified for a const span, but it can for a non-const span. This is just what that looks like. So here we have a non-const span. We're able to modify its data. Here we have a const span. We try to do the same things, and we run into these errors. OK. I will hand it off to Jasmine to talk about the usage.
Awesome. OK, we're doing great on time. OK, let's dive into the usage, where to use span. We've talked about the definition and such. So like Prithvi mentioned in the motivation, Span can be used as input arguments, replacements for contiguous containers. So we kind of already saw this. We have like a C-style array, standard vector, right? We can replace that with a span. And in this case, it's a const span because all of the arguments on the left are also const. And with that, this change is not necessarily like free of code changes. Here we can see that on the left, we have the first foo array that takes in a size, right, that C-style array. We don't have to do that with if we're using a span there. And so just to reiterate, span provides that type erasure for individual container types. And with vector specifically, it removes the need to allocate that memory, which is nice. Span can also be used to pass around compile time contiguous containers. So if we take a look at this example, we have this function get error codes. It returns a const vector reference. And within that, we have this static const vector of int, right? And here, maybe like you would use vector. We would use vector because C-style arrays are kind of hard to pass around, or standard arrays need the size. And there's a bunch of reasons why maybe vector would be a good choice here. But in this particular case, also, we are using this this magic static here, and that has some runtime overhead as well. And so we can kind of just optimize this by returning a span in this case. And you can see we have updated that inner array to just be a static const expr int array here. And there's a variety of ways that you can sort of define this in the source file. So in that first example, we kind of added the const expr int array into the unnamed namespace and call it from get error codes. There's a variety of ways we can do it here where the header remains unchanged. And in a similar example, maybe we're not dealing with ints, but we're dealing with strings. And so we can actually return a span of string views in this case. Just wanted to throw that in there. So, okay, we talked about usage. Let's talk about unsafe usage problems. And you'll probably see a lot of parallels to what Prithvi had mentioned in the string view section. So, right, spans or views, they don't own their memory, and this can often lead to a dangling pointer access scenario, right? So if we return span from a function, we have this get span bad, returns a span. We have this vector within this method, and we return that vector as a span. But actually, as soon as this method executes, like when we hit that end brace, that memory gets destroyed. And so we have this const auto s here. That s ends up referring to invalid memory at that point. In a similar example, we have this get vector that returns a vector. And so once that get vector executes, s, again, refers to invalid memory. So once we try to access it in this for loop, we're unable to. And modifying a container after creating a span from it, this is very similar to Stringview, right? You don't want to change the underlying data. So we can create a vector, we can create a span from that vector, that's totally fine. But as soon as we insert new values into that vector, we reallocate that memory, and that gets, and so S now, that span refers to invalid memory if we try to access it. In a similar example, so if we return span from a class member function, we kind of already seen a similar example on the last slide, but we have this private member variable vector, and we have getVec that returns that vector as a span, and we have add, which modifies the vector, right? And so we can instantiate A. We can call a.getVect and set that equal to s, and so we can get that span, that's fine. But as soon as we call a.add, we change that underlying data, that memory gets destroyed, that s was referring to, and now if we try to access, if we try to access s, we're unable to. All right, and if we create a span from a temporary in a range-based for loop, generally this will, that memory will get deleted again, so we won't be able to access that. But actually, this has been addressed in C++23 and Clang 19 specifically, and here's a link to that paper. So essentially, that temporary, the lifetime of that temporary gets extended. So this actually works in C++23 and Clang 19, and There's a link to the paper if you're interested and some additional details about the compiler support as well. But going back to that, we could just instantiate a prior to the for loop, right? And then we could access that span, and that would totally work. Okay, so sort of talked about where we can use it, some of the issues. Let me reiterate some of those in this best practice slide. So, right, we know we can use it as a function, as a replacement for a contiguous container for the argument. We can use it as a return value of a function, but only when we're sure that the memory is backed by storage. That will remain unchanged. Globals, right, get error codes that we saw on the other slide. Don't store it as a member variable of a class. Generally don't use it on the left side of an expression to store the return value of that type, right? This can lead to dangling pointer access scenarios. Generally don't use it to hold, don't use span to hold non-const containers in local scope because it may get modified, right? So that vector we saw on the previous slide, we can create a span as soon as we try to modify it. That memory gets deleted and that span is accessing invalid memory. And lastly, since it's low overhead and cheap to copy, like Stringview, pass by value instead of a const reference. Okay, so to wrap up the span section, let me just talk about some of the similarities, right, explicitly between Stringview and span, and some of the differences as well. So both of them refer to a contiguous sequence of elements, starting at position 0 with standard operations. Both are lightweight, easy to copy. They both have a pointer and a size. But Stringview is a read-only view over strings, characters, right? It's always constant, and it cannot be used to modify that referred string. And it supports string-like operations. But span, on the other hand, right, it's a view over a contiguous sequence of any element. It could be strings, it could be characters, it can be integers, whatever. And we can have non-const spans, which modify the contents. We have const spans that can't. And span is just a generalized view on containers. It doesn't have specific utilities or string-specific utilities in particular. And so, you could think of an example like span of characters, right? It's very similar to a string view, but in that particular case, we don't have the string-specific utility, so it's not particularly useful in that regard. And so if you do find yourself in that sort of position, and you're deciding which one to use, definitely use Stringview, because it's the best type for dealing with strings. And with that, I'll pass it back to Prithvi.
Okay, lovely. So that was Stringview and span. We're going to try to walk through a practical example of these. So our case study is going to talk through these pieces of code. So the first function we're going to look at is this function called getKnownHost. GetKnownHost returns a vector of strings. The strings in question here are Bing.com, Microsoft.com, and SharePoint.com. Then we have a class definition here. So this is the class A. Within it, we have this variable hostInt map. And we have this function isInMap that takes in a string host and checks if that string is contained by our hostInt map. Notably, hostInt map is a map of strings to integers. And then finally, we have this function hasKnownHosts. hasKnownHost takes in an instance of our class A. It uses the anyOf algorithm to basically check all of the three strings in the vector returned by getKnownHost, and it checks if any of these hosts are within the hostInt map of this instance of A. So it uses isInMap on each of the three hosts and checks if, uses the anyOf algorithm to see if any of them are in the corresponding hostInt map. Okay, so the first thing that we can optimize is we can use span in Stringview, right? That's what we've been talking about for the last 50 minutes. We might as well start there. And so what we can change is instead of having a vector of strings, we can have a span of string views. And from there, we just wanted to highlight that the const there that we've added is needed. Otherwise, you get the following compilation errors saying that there's no viable conversion between the return type of the string array or string vector and the actual return type of the function, the span string view. So now that we've made this first change, right, we have this span of string views being returned by getKnownHost, we actually immediately run into errors. So the first error we see is that there is no viable conversion from the const string view to the const string. Specifically, it points to this piece of code within hasKnownHost. It's highlighting this a.isInMap of host. And that's because in this function, we are looking at the string views that are being returned by getKnownHost now, but we're calling a.isInMap, and a.isInMap asks for a string, right? It doesn't ask for a string view, so we're getting this issue. A fix that we could do is we could explicitly convert to a string. That kind of sucks though, because we're trying to avoid that memory allocation at runtime. That's kind of the whole point. So instead, let's take a step back and let's see if instead we can change isInMap to take in a string view. So now inside hasKnownHost, we're looking at a span of string views. We call a.isInMap with each of the string views. This is fine because isInMap takes a string view. But actually it doesn't compile. And that's because of this error. It says that there's no known conversion from a string view to the const key type, aka the string. So now what's happening is we're inside isInMap, and we're checking containment with the string view that's being passed into isInMap. But we're checking containment inside of a map where the keys are all strings, right? And so it's saying that there's no conversion between string view to string. We know that that's like not explicit. Of course, the first thought maybe is that we can change the map keys to string view. That's not going to work because string view doesn't own its own memory, so we can't use it as keys inside of our map. Instead, we could do a string conversion, right? We can always come back to that. But once again, we want to avoid that, right? It works, sure, but we're allocating memory. That's what we're trying to avoid in the first place. If we were to do this, maybe we should be using strings in the first place. Why optimize this code at all? So instead, let's again take a step back and look a little bit further into the error we were seeing before. So a little bit further down, we see this is transparent was not satisfied thing. Does anyone have any ideas like what we could maybe add to fix this specific issue that we're not satisfying this is transparent? Whoa, what was that? I can't, oh yeah, was that you? Go ahead, what did you say? I couldn't hear you. Exactly, yeah, we can change that less. So instead of using the default, we can use a transparent comparator. Thank you. And so when we use a transparent comparator, this is what it looks like, right? So our map has a key type, a value type, and then we have this like std less, and we're overriding the default to instead use a transparent comparator. That third like parameter when you're initializing the map is the compare function. That's the thing that's used by like contains, find, count, anything that requires any sort of comparison. And so this works. This actually solves the problem that we were looking at. Just to walk through why it works, it's because it's allowing the following to work without allocating additional memory. So here we're checking contains with a char star. We are also checking contains with the string view. And of course, this was working before as well. We're checking containment with the string. And all of these cases are going to work fine now that we have the transparent comparator. In the case of string view, the reason it works is because the following two like bools over there, they compile. So the way that the relationship between string and string view is defined is such that string is less than string view and string view is less than string. I also want to note that I mentioned that these first two cases, right, this char star case was working. It would actually have always worked because there's an explicit conversion between string view, char stars and strings, right? Like that will automatically happen, but using the transparent comparator actually allows that to happen without allocating additional memory. Right now, we're not taking these char stars, allocating memory for them as a string, and then checking that comparison. It's working for the same reason that string view is working. And so now we have our optimized solution. So we started off with a getKnownHost that returned a vector of strings. Now we have a getKnownHost that returns a span of string views. We've also included the transparent comparator so that we can check containment of these string views inside of a map where the keys are strings. And then finally, we've made a couple of cosmetic changes here and there to just get this working. So this is great, right? We've optimized our code. There's no runtime memory allocation for string because we're using Stringview, and vector because we're using span. Okay, hand it back to Jasmine to wrap it up.
Thank you. Okay, let's talk about some key takeaways. So if you leave this presentation with anything, I hope it's these few points here. So if you have a const string, a const char array, you can convert that into a string view, like so. If you have a non-constructor function that accepts a const string reference, you can consider whether you can convert that into a string view. It may not work in your case or be as useful, but something to consider for sure. And you do want to remember that if you do end up converting it to a string later down the line, there is that memory allocation. And lastly, if you intend to convert to a const char star from a string view, please keep in mind that the data for string view does not behave the same as C star for string. Always assume that what you get from data does not end with a null character. You want to check if it's empty before using data because it can return null, and ensure to check the size as well. Yeah, I hope this helps you plant the seed in your mind to potentially use Stringview in the future. Here's some links to some articles, references, and such. And we just want to say a special thanks to Victor, who's sitting right here. Thank you so much. We appreciate the support. And here, I just linked some of the Stringview and span talks. And Chandra also is our colleague at Microsoft who we work closely with. And without the support and encouragement from these two folks, we certainly would not be here standing on the stage. And yeah, thank you so much for coming to our first CppCon talk. Okay. Yeah, we actually have 3 minutes left, which is surprising.
Huge turn of events.
Yeah, we can open it up to questions, comments, feedback.
So is it possible when you're talking about empty and if the string view is empty, does its data always return null, or it can be an empty string with actual valid pointer?
So do you mean, so you're checking, I'm just going to reiterate this back to you. So you have a string view, you're saying it's empty and you're checking empty.
Yes.
Are you asking if data is always going to return null?
Yeah.
Or some content? I believe it will always return a null pointer, which is why we recommend that is empty check and then using size.
Right. If it's null, it's definitely going to be empty.
Right.
But it is possible. Just thinking back to old C-style strings, it's possible to point to a memory that just contains a null terminator. In that case, it's an empty string, but the actual pointer is valid.
Okay, yeah, that's a good point. In the when we were talking about the literal operators, and you were able to kind of get these null terminators embedded within the string view. I actually would have to test that out. I haven't done that before, but it is an interesting point. I wonder if you would just have a null terminator or two, and then you get that information out from data. Yeah, so I would have to test that one out.
Oh, yeah,
you know off the top of your head.
No, I don't.
Thank you.
Yeah, thank you.
Yeah, that's an interesting one.
Thanks for the talk. I've got a couple of questions. But, so regards to when we were optimizing for the map thing, it is a map thing where we added the transparent less operator to make sure we don't do the allocation to actually check the map. Do you know if there's any sort of thing for unordered map as well?
Oh, I actually haven't looked into that. Okay, yeah, unfortunately. We specifically looked at it for the purposes of this function. Yeah.
Oh, that's fair enough. My other question is, so in one of the slides where you showed Jasmine showed where you can create a span from a const expression of an array. In a similar slide for Stringview, you actually did the const expression of Stringview directly. So, const expression Stringview name equals an actual string literal, but you haven't done the same thing for a span. Is that not possible? Just assign it directly rather than create an array and then sort of have another line.
Oh.
Yeah, like that in get error codes. If it's rather than
That's a
have an
good
int
point.
array and then have a span later, could that const expression int be just const expression span int?
I am not sure. I have to try it out, actually. We can chat after if you're
Okay.
curious. Yeah, I don't know off the top of my head. I'm sorry about that.
Oh, sorry.
I don't know if anyone else does. but-
One last question.
Go for it.
So in one of the very early slides, you showed Stringview had 4 constructors.
Yeah,
If I remember correctly, the first one is empty. The second one is a copy
it's
constructor.
a copy, yep.
The third one takes a char star and a length.
Yep.
And the last one takes a null terminated char star. Right. As in just char star by itself.
Yeah, it's just char star.
Yeah. In a few slides later, you showed constructing a string view from a string with a string.begin and string.end.
Yeah.
I just wanted to ask which constructor that calls.
So that's actually in, so this one, right?
Is it this one?
So in C++20, there was a new constructor, basically. And so it allows you to specify the begin and end.
I
And this
see.
is specifically in C++20, right? Yeah.
Cool. Thank you.
Yeah. Thank you so much for your questions.
Got about 20 seconds if anyone wants to jump up there.
So my guess is the reason you know all about the string views and so is that you were converting source code at your company to use this. Did you find improvements in memory usage or efficiency, or was that not measured?
We haven't measured it so far. We initially started looking into it because it became part of our code review system. So like part of our like pull requests like review system now is to check for things like this if there's like space to use string view or span instead. I don't think we have actually ever measured the performance of like one versus the other in our edge builds.
No, I don't think so because we haven't converted everything, right? We're just sort of moving forward. Any new code is added, we're using Stringview if it is applicable. Because we used to use context for like char arrays like constantly. I think that was the main thing. So for that in particular, moving forward, we're just using Stringview. So no, I don't think we actually have measured yet.
And
but-
how often do you inadvertently use it incorrectly and go, oh, good thing the compiler caught that, or it crashed, or has it been fairly robust?
Yeah, this has come up actually.
This-
there are like
yeah.
different opinions across our team about whether this works seamlessly or whether you run into tons of issues where suddenly it needs to be a C string and what have we done? Honestly, for me, it's been pretty seamless so far. Like I feel like I've used it mostly in like single use cases where I just need to read and compare. I know that like Corey, for example, on our team felt very strongly that there are a lot of situations where he suddenly is like, oh man, like this null terminator, like not having that guarantee is requiring me to like change a lot of stuff.
Yeah, I think there have been a couple instances where Stringview was used. I know of one in particular where it was used, it seemed fine, and then a crash happened later down the line, right? And then it was realized that I think the underlying data ended up getting changed, which caused issues that wasn't caught. And so, yeah, that like went in and then we realized that it crashed later. So yeah, it does happen. And I think it can be tricky to keep all of these things in mind too. But yeah, to answer your question, we have seen it for sure.
Thank you.
Thank you.
Amazing.
Yeah,
All right.
thanks all.